Hey guys, welcome to your second part for covalent bonding. In the first video, we really talked about and focused on the Lewis structures of covalent bonds. Now we're going to take that information and apply it to a couple of other things. We're going to talk more about what we physically see when we see covalent compounds, and really just focus on how we name covalent compounds. I know that in the ionic video, I packed a lot of information, so this happened to be broken down into two parts, and I think that's okay. As with any video, if you have any questions, please make sure to ask. You guys are really good at asking questions, but if you don't understand something, please reach out. I want to make sure that you guys all are getting the information and able to use it in a good way. Like with ionic compounds, we see that covalent compounds also have physical properties. Reminder, physical properties are things that we can see, we can measure, we can touch, we can evaluate with our naked eye, and so it's a lot easier to identify different compounds based on not just if it's a metal, non-metal, or non-metal, non-metal, but really how they act in the lab. We'll see this in the lab when we compare ionic and covalent compounds in the next few days. But things you should look out for when we are talking about the physical properties of covalent bonds would be that they have low melting points. If I take a covalent compound and put it in a pot, it would easily melt at a very, very low temperature. As a reminder, high temperatures for ionic compounds are things like 1,000, 2,000 degrees Fahrenheit. And when we look at covalent compounds, those melting points are going to be anywhere from 50 degrees Fahrenheit to 200 degrees Fahrenheit. So keep that in mind, that I know 200 degrees Fahrenheit is extremely hot to us. When it comes to compounds, that's not very high when we relate that to ionic compounds. When we look at the state of matter that we see covalent compounds in, they can be in all forms. Reminder, ionic compounds are found typically in a solid form. When we see covalent compounds, we're going to either see them in solid, liquid, or gas. It really truly depends on the compound. So the state of matter is not a super reliable way to identify a compound. The other thing with covalent compounds is that they have little to no conductivity. So when we take our conductivity probe, it's not going to ping very high at all because we cannot, there's just not enough as far as the charges go to allow for a conductive current to flow through. The other thing with covalent compounds is that they are not soluble in water. There are some exceptions to this, and I'll talk about that more in class, but something like oil is considered a covalent compound, and if we take oil and put it in water, we know that it floats. So that would be a good way to demonstrate how it is not soluble in water. It is soluble in non-polar solutions, but when it comes to water, it is not soluble. Again, there are some exceptions to this, and we'll talk about that in class. The other thing with physical properties is that these are soft and flexible. You can typically break these very easily, whereas ionic compounds are hard but brittle. Covalent compounds are not. They're pretty soft. You can typically break them with your fingers or hands. So keep that in mind when we compare them. They're very much opposites. Briefly brushing over something that we've already talked about with polyatomic ions. We've talked about naming them. I've given you a chart. The only thing I wanted to talk about when it comes to polyatomic ions is that they are a group of covalently bonded atoms, as in we have two non-metals together that come together and create a charge or have a charge. So when these two non-metals covalently bond, it carries an overall electrical charge. And so that's what you see. Example with this NH4, we see nitrogen and hydrogen, both nonmetals, but bonded together have that actual electric charge. And so again, you have a table that is going to be very useful for you as you proceed on with this unit. When we draw the Lewis structures, the only exceptions that we make is that we count the number of electrons that are present within the charge. So here, I just erased it, but this was a plus sign. NH4 plus, that indicates that I am losing one electron. So when I count the total number of electrons, it would be 5 plus 1 plus 1 plus, I lost track of my ones here. +1, +1. Either way, there's 4 ones because I have an H4. So 5 + 4 is 9. However, I had a +1 there, so I have to subtract that to give me a total of 8. So to show this charge for NH4, I'm going to be surrounded by 4 hydrogens, and I'm not going to have an extra electron because, again, I've lost that due to that charge. Another thing that you use when you represent polyatomic ions is you always use brackets. So the entire Lewis structure would be in brackets, and then you would put the charge outside of the brackets. So this would be an H right there. So that's the only difference in the Lewis structures of polyatomic ions versus just normal covalent compounds, or excuse me, normal covalent bonds, is that you just add the brackets and the charge. Really, the brackets are there just for a formality, just as a reminder, and recognize that NH4 by itself has 9 electrons, but with the charge, we are losing that 1 electron. This particular slide, I went back and forth on trying to decide if I really want you to know this, but I do think it's important because a lot of times when I do a Lewis structure, you guys quickly erase if yours doesn't look exactly like mine, but I thought it was important to remind you that we can do things in multiple ways. And so we have what's known as resonance structures. Resonance structures are Lewis structures that can be drawn for a molecule in more than one way. So an example would be O3. If I draw out my Lewis structure, so here's my O, and I put all my lone pairs in, we know that that's more than 18. So O3, 6 times 3 would give me 18. So what I need to do is I need to create a double bond. So I'm going to go ahead and take away this pair here and this pair here, and I'm going to share a set instead. So if I share that set, that gives me 2, 4, 6, 8, 10, 12, 14, 16, 18. So I now use a total of 18. However, you'll notice that I put the double bond here. I can also have this same structure, if I erase this whole thing, my apologies, I can do that same structure, but my double bond is now on this side instead of this side. So that's what a resonance structure is where we just have a movement of our double bonds or triple bonds in some other place. Still the same compound, but I just have a different Lewis structure. It's drawn differently. So I thought it was important that you noticed that it doesn't have to be identical, and there are different ways to do these structures. So you just got to give yourself a little bit of flexibility. Finally, naming covalent compounds. Now, I feel like you guys did a very nice job with naming ionic compounds. You really didn't struggle too much with that because, I gave you your chart. You guys picked up on the "ide" at the end, and that's good because you'll see that again. But there are a couple more rules when it comes to naming covalent compounds. So I did list them here, and they are also in your notes. The other thing that you need to be aware of is that we use prefixes. Prefixes are going to be really important for covalent compounds. The prefixes indicate how much of something I have, how much of the element that I have. Unlike ionic compounds where you reduce, so for example, if I had Fe2O2, I would reduce that to have FeO. In covalent compounds, we do not reduce. We absolutely keep those numbers because those numbers tell us the actual name of the compound. So it's really important. So if I had something like C2H6, I now have to use prefixes to indicate how much of these elements I have in this particular compound. Another reason for that is because I have C2H6. If I reduced everything down, I could create a CH, but there are a lot of molecules, a lot of covalent compounds that have a CH in them. So the numbers, the prefixes tell me how much of those compounds. Every compound is different. So C2H6, made of the same things, different numbers compared to CH4. C2H6, CH4 are not the same thing, even though they're made up of the same elements. So hopefully that makes sense. All right, so the first rule when it comes to naming covalent compounds is that the nonmetal only gets a numerical prefix when there is more than one. So you're always going to name both nonmetals. The formulas will be given to you. You're not going to come up with the formulas on your own, just like random. They will be given to you, or you'll be given the name. So you'll have information. But let's say I am talking about CO2. The first non-metal only gets a numeric prefix when there is more than one. So if we look here, this is my first non-metal. It is carbon. If you notice, there is no number here. If there is not a number there, I do not have to have a prefix in front of the element. I would simply name the element. So in this case, I would have carbon. So no prefix if there's only one. The next rule, the second element always gets a numeric prefix and always has a suffix "-ide" at the end. The "-ide" is not new. We did that with ionic compounds. So keep that habit up. But it says you always use a numeric prefix. In your notes, you'll see that I have added those prefixes into your notes. I didn't put them on the slide. I just didn't want to take the room because I knew I'd be writing on the slide. So if I look at how many oxygens I have 2. So I have to use the prefix "di." So I'm going to put a "di" in front of my oxygen. But again, I need to add an "ide" to the end. So instead of saying dioxygen, I would say dioxide. So CO2 is known as carbon dioxide. We can do another example of this. Let's say I'm just thinking of something random, CO. Again, C does not have a number after it, so it does not need a prefix. You would just simply say carbon. But in this case, oxygen also does not have a number. However, my second rule says the second element always gets a numeric prefix and always has a suffix of "-ide." So even if there's only one for the second element, you would still have a prefix. So in this case, I would put monoxide. Mono is the prefix for one. I'm going to go ahead and do one more for you just to make sure you're following along. And if you're not, it's okay because we're certainly going to practice this in class. We always do. But I just want to make sure that you're doing okay. So if I have NH3. Also keep in mind that some of these covalent compounds have their own identifying name that's not what you would typically use. For example, ammonia, ammonium, you'll see that too on that prefix list. So we do have those to reflect on as well. But just for the naming purposes, we're going to get in the habit of naming using our prefixes. Again, in this case, nitrogen is by itself. So this is just going to be nitrogen. And then the H3, I would look up my prefixes in my notes, and it says trioxide. So this is nitrogen trioxide. I want to do one more. One that has multiple first elements. So let's do N2O4. And this is from your notes. If you're looking at the notes, you'll see now I have 2 nitrogens. So now in this case, the first element does have more than one. So I need to use my prefixes here. This would be dinitrogen. And then the O4, if I look up 4, that is tetraoxide. And that's it. I know that it can seem kind of weird, but once you get used to using the prefixes, it really just remembering those rules is the only thing you really have to work on. As like always, if you have any questions, make sure to ask me on Edpuzzle. Bye.